Hi everyone. In this video, we'll see how blockchains work under the hood. So, blockchains are basically open, immutable, distributed ledger of transactions. Now, that was a lot packed together. So, we'll dissect it one by one. Open means that blockchains are publicly accessible, which means anybody can join it and anybody can read their data. Most of the blockchains are public, but they can also be private sometimes. So, it's just like internet and intranet. Then blockchains are immutable. Immutable means that blockchains can't be tampered with easily. Once the data goes into the blockchain, it's almost immutable. Almost immutable because they are cryptographically and crypto economically very hard to tamper. If I were to summarize that, it simply means that blockchains can theoretically be tampered with. You can change the past data, but in order to do that, you'll have to spend so much resources that it doesn't make sense economically for you to be trying that out. So that's how blockchains become immutable. It's not like they are hack proof. You might have already heard about many blockchains getting hacked. Um there was the famous DAO attack, and other hacks happen time to time as well. But the system design of blockchains is such that it makes it irrational in a way for anyone to hack it. Then blockchains are distributed. Distributed means that the blockchain state is hosted and maintained by a network of nodes instead of like a single server. So, in general, if you take your own machine for an example, there are some CPUs, there's some hardware going on, and you have an operating system running on it, and the entire state of your machine is stored in your hard drive. So, you have a single hardware unit maintaining a single state. In blockchain, what happens is the state is a common state that is maintained by a distributed nodes that are peer-to-peer connected. So all of these nodes keep a copy of the state with themselves and they update the state collectively. We'll talk about it in detail in a later video. Lastly, blockchains are ledger of transactions, which simply means that blockchains are a record of many transactions which simply denote that A sent something to B, like it could be a token, it could be an NFT, it could be any kind of asset. So blocks are the core component of blockchains, and a block contains multiple transactions of type A gave something to B, and these transactions, along with some other metadata about the block, is put into a hash function which creates a hash from that data. And that hash function is basically used by the next block uh, to cryptographically reference its parent. So that's how a chain of blocks is formed. And as more and more blocks are added to the chain, it becomes harder and harder to tamper with the historical data. We'll try to understand this with a simple diagram. You can see that we have three blocks here in our diagram, and each of these blocks would contain multiple transactions. Now, when you put together all of these transactions and some other metadata about the block into a hash function, which is generally a Kachak 256 hash function, it could be something else also, depends on the implementation. But the underlying concept is that this block data, which contains transactions and some block metadata, it is put into a hash function which generates a constant size hash like this we have here. So you put together all the block data into a hash function and you get a hash for each block. Like we have this for block 1, we have this for block 2, and this for block 3. And the way it works is that each block cryptographically references its previous block. So you see that the previous hash for block 1 is 0 because there's no block before it. These blocks are called genesis blocks. But when you see block 2, the previous hash for block 2 is the hash for block 1. And this is also a part of the block data. So the metadata that I mentioned earlier, this is a part of that. So when you are creating a hash of this block, this is a part of block data. This is put together with other transaction data and some other block metadata. and that's how this hash function is generated. So let's say if I were to tamper with the data of block 1, this hash would change, and if this hash changes, then this hash also has to change. So that's how it's become increasingly harder and harder to modify the blockchain once many blocks are added in front of a particular block. So similarly, block 3 also, just the way I told you about block 1 and block 2. Similarly, for block 3, all of the transactions along with the previous hash of block 2 and some block metadata, is put together into a hash function, and you get a hash for this block. And the chain continues this way. Now, there are two other main components in blockchains, which are nodes and consensus mechanism. These form the network part of the blockchain, or you can say the distributed aspect, where nodes, which are sometimes also known as miners or validators, these are responsible for checking the validity of transaction and adding them to the network. By validity of transaction, we mean that they check whether the transactions are good to go or not. Like someone is not trying to hack anything. There's no double spending happening. Like a same amount of money is being spent twice. So the person is basically, person has, let's say, $10, but they are spending 20 in two different $10 transactions. So that is double spending. They check for that, and they check for other malicious transactions, like someone is trying to game the system or not. And once they are sure that the transaction is valid, the block is added to the network. Now, nodes use a consensus mechanism to accomplish a distributed agreement between them so that they can prevent an attack on the network. So, as I mentioned earlier, multiple nodes together maintain the state of the blockchain. So, if you are trying to update the state of blockchain, one node will update the blockchain, and they'll transmit this data to multiple other nodes in the network, and all of them would try to validate the state changes. And once you get a green signal from all of the other nodes, or depends on the algorithm, sometimes 66% of the other node, you are good to go. So once multiple nodes in the network have validated the transactions, then only it's added to the network. And these nodes use consensus mechanism, generally called proof of work, proof of stake. And there are some other niche algorithms as well. The nodes use this consensus mechanism to arrive at a consensus whether to add a new block to the blockchain or not. So now we'll summarize everything we have learned so far by using a diagram, and we'll walk through the process one step at a time. So a new data, that is a transaction, is entered into the blockchain. Then this transaction, along with some other new transactions, are accumulated and put together in a block that represents those transactions. This block is then broadcasted to all of the nodes in the blockchain network, where each node validates the transaction on their own and give a green signal or a red signal that whether the block is good to go or not. And once the block is approved, it is added to the new chain permanently. And again, as I mentioned before, once multiple blocks are added in front of that block becomes harder and harder to tamper with. So now I'll show you a demo of how this process works. This is a very good site by Anders Brownworth. You can go to andersbrownworth.com and you'll be able to find this demo there. So the first demo is of a hash function. So remember that in a hash function, you put in an arbitrarily large amount of data and you get a constant size hash as an output. So let's say if I type this is a good day, I get a particular hash out of it. Now, if I modify it slightly, you see that the hash completely changes. So each hash is unique to the data that is passed into the hash function. And there is very, very low probability of deriving same hash for different data. Now, if we move on to block, remember that I mentioned that transactions along with some other metadata is a part of the complete block data. So generally, you'll have some other block metadata depending on the blockchain you are using. But the gist is that there's some transaction data which is put in here. There is a nonce value which represents different things, and you have the block number, and you have some hash value generated using this data. So again, let's say if I type in some transaction data, we get a hash value that is a representative of the entire block data, that is the block number, the nonce, and the data. So you get a hash out of all of this. If I were to change this, you see that the hash value changes completely. Or if I were to change nonce value, you see that the hash value changes completely. So this hash value is generated using all of the block data, and if any of the block data is changed, the hash value changes completely. Now we'll see how this plays out in a blockchain. So we have our first block, and there's some random nonce, and I type in some block data. I just type in block 1 for ease, and I'll mine it. So you see that we have a hash generated, and the previous hash of the second block is same as the hash of the first block. So that's how, if you remember, that's how a block cryptographically references its parent, because this hash of first block is now a part of the block data of second block. So I'll add some data and mine it, and all of these things, the block number, the nonce, the data, and the previous hash, are put together into a hash function, and then we get this hash. Similarly, for block 3, we have it referencing the block 2 using the hash of block 2, and all of the block data is put together in a hash function, and we get a hash of block 3. So it's as simple as that. If I were to change the data of block 2 and let's say make it 4, so it breaks the chain because now the hash is changed, and this block would be referencing the previous state of the second block because it has a hash for that. So that's how you can detect that the blockchain has been tampered with, and that's how it becomes increasingly harder and harder to change the previous state of the blockchain as more and more blocks are added to it. Now we are clear with the way hash functions work, the way a block is hashed, and the way a blockchain is formed. The last aspect of this demo is how it works in a distributed environment. So you have different nodes maintaining a record of the blockchain, say peer A, peer B, and peer C. So you have all of these maintaining the record of the blockchain. So similar to last example, we have a blockchain formed using this data. So all of these nodes would keep a similar copy of the blockchain, and whenever a new transaction or a new block is added at the end of the chain, all of these peers, all of these nodes would try to validate that transaction, and they'll check it against the previous block data. So let's say if one of the nodes of blockchain is a malicious node and they try to change the previous data, let's say peer B is the node that wants to game the system. They want to change the history of blockchain in their favor. Let's say they want to add a transaction that pays them something. So when they'll try to change the state of the blockchain, they'll have to propagate that changes to the other peers like the peer A and peer C. Now when these nodes would get this data, they will compare it with their own copy of blockchain, and they can easily identify that B is trying to do something fishy. So they'll instantly reject that, bro, this transaction is not valid, this block is not valid, we are not going to accept it. And that's how the blockchain is saved from nodes that are trying to hack it. So that was a very high level overview of how blockchains work from a first principle. Each blockchain is built for a specific purpose, and the exact technical system design varies from blockchain to blockchain. It mainly depends on the problem that a particular blockchain is trying to solve. Like we have many different blockchains out there. Bitcoin is very well known. It's a store of value, so it is a simple ledger of transactions. Then we have layer 1 protocols that support smart contracts. So you have Ethereum and Solana there. Then we have some layer 2 protocols which are built on layer 1 protocols to increase the transaction per second, the throughput of the blockchain. So they are designed differently. And then we have some other layer 1 blockchains like Zcash, which is privacy focused, Filecoin, which is focused on storing data in a distributed way. Uh, so there are different kind of L1s there as well. And we also have a category of layer zeros. Layer zeros are basically blockchains that sit below the layer 1 blockchains, and they allow different layer 1 blockchains to be connected seamlessly on a single network. So we have Polkadot and Cosmos blockchains operating in that zone. So now you see that there are multiple blockchains, each trying to solve a different problem, and hence their technical designs and exact specifications vary from each other. But the fundamental principles remain the same that I explained in this video.